Hola a todos, welcome to this talk about advanced performance tips and tricks from a Unity consultant. My name is Nicolas Borromeo. I'm a senior software development consultant here at Unity, and my job mostly consists of analyzing Unity clients projects, seeing what the problems are, and addressing them with actionable advice. So I'm here today because we want to do a continuation of last year's talk, Unite 2024 Performance Tips and Tricks from a Unity consultant. But today we are going to deep dive into some other less frequent but interesting areas of performance. So today we are going to deep dive into graphics performance, some more tips compared to the ones we saw last time. Then we are going to deep dive into editor performance and how to make the editor work faster. And finally, we are going to discuss how Unity loads assets, meaning scenes, addressables assets, and whatever Unity loads, how to profile it, and how to improve it. So let's start talking about graphics. And one of the most common topics we see, at least in mobile games, is the use of intermediate textures. The idea is that under certain conditions, Unity might render into intermediate render textures instead of rendering directly to the GPU back buffer. And aside from missing some platform-specific optimizations when doing so, also this involves a costly bleed at the end of the render graph, meaning that you need to copy all the information, all the color information you put into intermediate textures back to the GPU back buffer to display that, and can cost 1, 2, even 3 milliseconds in expensive scenarios in mobile devices. So you can realize if you are suffering from this situation by using either the frame debugger or the render graph viewer to detect if the two conditions happen. If one of the render textures that your render pipeline is using is called something like camera something attachment, could be camera target attachment or camera depth attachment, that's a sign that you are rendering into intermediate textures. And also, if you see a bleed pass at some point where you copy the information from the intermediate textures to the back buffer, that can be a sign of that. For example, in the screenshots at the bottom of the slide, you can see in the right-hand side the render graph viewer. And you can see how there are several render textures, but two of them are called camera target and camera depth attachment. And you can see how in the highlight passes, bleed post-processing and final depth copy, we are reading from the camera target attachment, hence the green rectangles, and writing that back to the back buffer color and back buffer depth textures, meaning that given the red rectangle, we are writing to them. So if you see this scenario, you might save some performance depending on certain conditions. So the idea is that Unity might need the intermediate textures for lots of different reasons. For example, it can be some setting in the SRP asset settings, some render feature that you are using that requires that, or even some material settings depending on the pipeline. So here is a non-comprehensive list of stuff that can enable either color intermediate textures or intermediate depth textures. But I'm going to give you something better, how to get to know which of these conditions is applying to your specific project. So the idea is that you can essentially breakpoint the SRP, essentially the URP or the HDRP source code in the line that decides that. Essentially, the SRP or URP and HDRP source code are very easy to read, and I encourage you to do that. So for example, to realize if we are using intermediate textures, if you are using the URP render graph version, or the latest URP essentially, you can breakpoint the requires intermediate attachments method in the universal renderer class. Or if you're using older URP versions or newer URP versions in the compatibility mode, you need to breakpoint the create color texture and create depth texture variables in universal renderer. So let me show you an example of this. So I'm here in the universal renderer, the render graph version of that, the latest version, requires intermediate attachments. I have attached a rider into Unity. And in this case, I will try to check whatever modifies the required color texture variable. So let me put breakpoints here, here, and here, just after the execution of these lines. And if we go to Unity, you will see that the breakpoints are immediately hit because, of course, the editor is still using this to render. And we can see that if after executing the first line, we can see that the Boolean is false, so we can continue. The second one is false, so this method didn't do anything with that. The third one is false, again, no problem. And as you might imagine, the next one, this one here, it's saying true, meaning that this method right here was the culprit. So essentially, we can try again this, but by putting breakpoints in this other method. And we can put breakpoints in essentially wherever we return true. Here, here. Let me just remove this. Here, and here. So we can see that now this return hit, and we can see that the first variable of all this condition is the culprit. You can already see all possible other conditions that could trigger this. And if we research what enable requires bleed for off-screen camera, we can see that post-processing enable is true. So essentially, post-processing is one of the most common cases where you use intermediate textures. So of course, most PC games will need that. But in some mobile games, you might not actually need that and save some performance back. So that's regarding intermediate textures. Let's discuss now other little topics like, for example, post-processing volumes. Remember that in Unity, you have the volume framework that defines areas in your scene that can apply different post-processing profiles. The idea is that Unity will recognize where the camera is, which volumes is touching, essentially, and will combine the post-processing volumes profiles to generate a final post-processing effect. The idea is that we update this constantly because the camera can move constantly and touch different volumes. But if you have the classic scenario where you have a single volume, which is global, which has the same setting all along the entire playtime, you can disable this slide. It's not taking a lot of time, but can depend according to the mobile device. So essentially, if you don't want to pay the price of updating volumes, you can essentially open the Universal Render Pipeline asset, enable the advanced properties in the three dots buttons, and then you will see a new option called Volume Update Mode, which by default is every frame, but you can change it to via scripting. This allows you to at least update the volumes if you expect some changes that happens sporadically, and again, save some little performance here and there. Then I want to discuss a little bit more about how to reduce render passes cost, specific render passes. So last year we talked about some passes. Let's deep dive a little bit more into them. So regarding the shadow maps, you can disable cast shadows in the renderers to reduce the amount of objects that are rendered in the shadow maps passes. But you can do a little bit better, and what you can do is to use the layer shadow call distances API. It's a property that is in each light that allows you to define essentially different far clipping plane distances according to layers. So you can create a layer for tiny objects and reduce the far clipping plane, so the shadow map camera will essentially cool those objects that are far further from that. So you can define, little, medium, and large size layers and define different drawing distances. And the same API exists for the regular rendering, for the camera rendering, which is layer cool distances. It's the same effect. Usually, one tries to cool using load groups, but if you're not using that, this is the next best option you can do. Then, specifically in HDRP, you have the dead prepass. Well, in ERP, you also have it, but at least in HDRP, you can do some little tricks to reduce its cost. So essentially, objects will render in the depth pass according to different settings. For example, if you're using forward rendering, essentially transparency materials in HDRP, or if you have alpha clipping enabled, or if you have receive decals enabled on those materials, essentially the objects needs to be in the depth pass, along with other conditions I didn't mention now. And the point is that, first, if you don't really need these checkboxes, you can simply get rid of them. But if you need them, but you are using load, what you can do is use the fully configured material for load 0, and then for other loads, load 1, load 2, load 3, disable these features because faraway objects won't, probably these effects won't be perceived in faraway objects. So you can save a lot of performance by selectively enabling features according to render distance. Then, another topic is scene roots. The idea is that several systems in Unity can essentially parallelize work if the objects are not under the same root. So if you have a classic scenario where you have a single game object being the root of your scene and you put everything inside that, probably lots of Unity systems won't benefit from parallelization. For example, the bonding volumes updating of renderers won't be parallelized in such a situation. Instead, if you separate the renderers in, not necessarily every renderer needs to be in the root level, but at least if you split them evenly between different roots, you can parallelize this work. Or for example, if you're animating, the transform writing essentially, when you animate, you need to write the transform of the bones or whatever you're animating. this writing of the transform properties can be parallelized again if the renderers or the animators are not in the same root. So essentially, at least for dynamic game objects, objects that moves and need to update constantly things based on transformation, avoid the single root. Let me show you an example of this. So I have this exact scene, actually. So if we play and stop breakpointing URP, you will see that if we record a little profiler capture and we start analyzing the contents, we see about here that we have the update all renderers in the post-late update phase. And we have this little cost called schedule update renderer volume bonding volumes. It's a tongue breaker. So essentially, as of now, nothing is moving. So it's pretty fast. It's not too much to do. But if I record and essentially move the entire root like this, and then we profile those frames, we'll see that it started to take a little bit more, not too much, to be honest, but this is a simple sim. So you will see in some frames, actually, if we set this example, it's quite a big, actually. 0.2 milliseconds for this computer should be better, but still not that bad. But what I want you to see is that if I scroll and try to see what the shop threads are doing, essentially they are idling, they are doing nothing, because there's nothing to parallelize in this case. But if I take the contents of the root game object and put this outside, record, and move these guys again, these frames right here, we will look again for our update bonding volumes method. And you will see that now, if you scroll to the shop's threads, you will see that now some shop is happening here. So part of the work was split along different threads, as you can see right here. Simple trick and can save you a little bit of performance here and there, especially if you have very complex big scenes. So let's continue. And a last tip regarding graphics is the features available in modern mobile APIs like Vulkan or Metal. Essentially, the memory-less depth option in the player settings allows you to use the memory-less features of render textures. This is a feature that you can use for your own render textures or for the ones that Unity creates for you. The idea is that in these newer platforms, if you are aware of how mobile CPUs work, they use the concept of tile rendering. They have this little memory that essentially treats tile by tile in the rendering of the CPU. Essentially, all the render happens in these tiles instead of the entire screen at the same time. And the idea is that most of the times, once you need the depth information just for rendering objects in the correct order, especially opaque objects. And once the rendering is finished, most of the times you don't need the depth information. By default, both the color and the depth information is written back to main memory, to the regular VRAM of the CPU, instead of being kept on the on-tile memory. But again, most of the time you don't need the depth once that finishes. So if you enable memoryless depth, what will happen is that the CPU will only copy the color information back to RAM instead of the entire depth information, saving you a lot of bandwidth when writing back into the CPU and also a little bit of memory here and there. So yeah, you can essentially switch the memoryless depth mode to automatic in the player settings and let Unity decide for you, or forced if you are really sure of what you're doing. But well, by default, this is unused, so you will want to check it. So that's regarding graphics. Now let's talk about editor performance. And essentially, the idea is how to make the editor work a little bit faster for you to iterate faster. So aside from the great improvements that Unity 6.3 and Unity 6 in general had on top of this, there are some other things that you might want to do that essentially is in your power to do, which is, for example, dealing with splitting or merging assembly definitions. The idea is that whenever you modify a script or you need to essentially recompile your scripts, Unity will decide, or better to say, the C# compiler will decide which assemblies needs to be recompiled, and then the ones that doesn't have dependencies between each other can be compiled in parallel. So compilation also benefits for multi-threading. So considering this, the big thing, the best first thing you can start to think about is just to think about your dependencies of your assemblies. Think if you have unnecessary assemblies, essentially putting restrictions on the compilation parallelization. And if you have big assemblies, like in this example right here, the bottom left example, where we have a long assembly and there's other three assemblies waiting for that to finish, you have the situation where a single assembly is slowing down the compilation of every other assembly. Of course, if those dependencies are needed, you might think of, okay, maybe we can split this one, put it into two different assemblies, the code of this, if possible, if it makes sense for your scripts, and then a little bit parallelize this compilation and speed up your performance. But beware of over-splitting, because there's a small overhead that you need to pay for every single assembly, despite of the code it has. So essentially, if you have a situation like the other one at the bottom, you have 5 consecutive assemblies that might be related to each other, but they are split unnecessarily. By merging them, you can also save a little bit of performance back. So, of course, the decision between when to split, when to combine, need data. You cannot blindly decide that. So there's a third-party tool called Needle Compilation Visualizer. It's a package you can install in your project, which essentially shows you a nice timeline of how the assemblies depend on each other, how much time each one takes to compile, and yeah, essentially that. So let me show you this one in action. In this case, I already did the example. I installed the package, opened the window, and there's this little button, compile player scripts, that will take all assemblies in the assets folder and recompile them. So essentially, here you can see a simple case I did where assembly A have 3 dependencies, B1, B2, and B3. You can see how them are waiting for assembly A to finish. And assembly C is another assembly that has other purposes. But you can see that, for example, if you first you can put the mouse on top of the assembly A and see the exact time it took. And if you click it, you can see the assembly references. Here you can see how B1, B2, and B3 have a dependency on assembly A. So again, simple tool, but can give you plenty of nice information about what to do regarding compilation times. Now, the next thing that happened after compilation is domain reload. Everybody probably is suffering right now from this. Of course, in the future, we plan to implement this with Core CLR, but as of now, what you can do. First, we need to consider when domain reload is needed, and actually what domain reload is. Domain reload is essentially the act of essentially resetting the scripting state to allow for the new recompiled code to enter. So we need to do some cleanup. But you can avoid this cleanup, essentially, and your scripts, if your scripts are prepared for it, you can eventually not need it. So domain reload is executed after compilation. Always, you cannot skip the domain reload after compilation, but you can skip it before entering play mode. That's another domain reload we do that you can skip by going to the play mode options in the editor settings and say do not recompile, do not reload domain. But again, your scripts need to be prepared to handle scenarios about auto-cleaning the contents of static variables or static delegates and that kind of stuff. So what you can do in order to at least get to know which scripts might be a problem in this is check the project auditor's domain reload. Project Auditor is a Unity plugin that you can check in the Unity package manager since Unity 6. And before Unity 6, you can actually download it separately from the GitHub repository. And essentially, it has a domain reload sections with advice about possibly which scripts can have domain reload disabling problems. But then what happens about the recompilation that has mandatory domain reload? Sadly, you need to do domain reload, but sometimes after domain reload, you can have initialize onload methods that are executed. Don't confuse this with the runtime initialize onload methods. Runtime initialize onload methods are executed always when you play the game, but the regular initialize onload methods are executed whenever you reload an assembly. And sometimes, in some cases, especially if you're using specific third-party plugins, there can be costly operations that happen there constantly. So my recommendation there is just profile your compilation with Unity editor, with a native profiler like Superluminal, or by putting custom profiling markers in your initialize onload methods to realize if those can be the issue. So let me show you an example of this. So in this case, I will use the Unity profiler to profile in editor mode. So essentially, if you do this, you are profiling the very editor. Let me just, for now, extend the preferences to extend the number of frames this can hold. I hope my machine doesn't die from doing this. So, and while recording, I can go to compilation. And in this case, I prepare a simple case in assembly C, where if I recompile assembly C, we will have some trouble. So if I re-import this, you will see in the bar of recompilation, after this finishes, that domain reload is happening. And you will see that the initialize load method's time will be displayed here. About here, you can see how we are processing the initialize load method. It's taking a lot of time. So if we stop recording after that, immediately after that, before losing that information, and we go to the last frame, we will be able to see, not this frame, probably the previous one. There you go. Or the previous one. Ah, that's the one. So you can see here exactly what happened during the domain reload, with at least the things that Unity instruments. And if you check, there's one marker called process initialize on load method attributes, and here is where your initialize on load methods are executed. Of course, we don't have many information. We know that some initialize on load method is having issues. So remember, or you can either use the deep profile to get to know more information about what's happening here, or again, superluminal to profile the editor itself and get profiling captures from there. Or again, you can use custom markers in your initialize on load method to get more information about which method is causing the issue. So you can see here, in this case, I know this is the one because it's a very obvious problem here. But yeah, it was just a way to illustrate the issue. They need to go here. So another big problem is shader compilation times or shader variant explosion. This can affect several aspects of your game. So in last year's talk, Unite 2024, Performance Tips and Tricks from a Unity Consultant, we talk about the runtime compilation of shaders, essentially when shaders are compiled when you play the game, which produce hiccups and affects the performance. So we talk about the different tips about how to pre-warm the shaders. But today I want to discuss more the other aspect of shader compilation, which is the shader compilation that happens during builds. If you have long build times, it's highly likely that one of the possible reasons is that you have lots of shaders to be compiled during builds. Of course, in the first build, then in a pre-warmed build machine, this might not be a big issue. But at least for the first build, essentially, you need to consider that when you build, you are compiling every possible needed shader that your build needs. And the possible word is key here, because you might not need all of them. There are some shaders that you might be compiling needlessly. So the idea is that you will want to use different shader stripping techniques, which I'm going to talk about now, to reduce the number of shaders built. And this also will reduce the shader memory pressure when you are playing the game, and other things that we are talking later today. But in order to apply shader stripping techniques, you need to consider how keywords and variants are related. So essentially, remember that variants are essentially different versions of your shader with different scripting paths. Remember that the CPU is not very good at dealing with ifs. It can suffer from shader occupancy issues if you use too many ifs, and essentially performance of executing both sides of the if and the else, and discarding the unneeded results. So essentially, in order to deal with this, Unity creates different versions of the shader according to the features. So, for example, if you have a material that doesn't require normal texture, you have a version of the shader that doesn't have any normal calculations at all. And Unity does that by the usage of keywords, which are essentially compiler directive ifs to create the variants. And you have two different types of keywords that you can use to say, if normal maps are on or if normal maps are off, for example. You can define that via a keyword, and you have two types of keywords, shader feature and multi-compile. So both are similar in the sense that both create variants, but the thing is that shader feature generates variants according to the permutations of shader features your material uses. So depending on how your material uses these shader features, the number of variants will vary. I will give you an example shortly. But multi-compile keywords are different in the sense that regardless of the material usage, it will always generate all possible combinations of shaders to respect all possible variants for all the multi-compile keywords. Essentially, you will always generate variants for multi-compile keywords regardless of what you do. The idea is that these multi-compile keywords are intended to change in runtime. So Unity cannot predict what you can do and what you cannot do. So just in case, compile everything. So essentially, a little mathematics is the number of variants is essentially the number of material shader feature permutations multiplied by all possible permutations of multi-compile keywords. So to give an example, let's say you have a shader, which a single shader feature and a single multi-compile keyword, and both of them have the on and off status. Like you can see in the bottom, you can either have the feature on and the feature off, or you can either have the multi-on and the multi-off keyword. So the maximum possible variance for this case is 4, right? But you can see that if you have, for example, one material with the shader feature on and one material with the shader feature off, you will have all possible combinations, 4. But if you have material A and material B, both with the shader feature on, you can see that you have a single combination of shader features. Both materials have a single version of the shader feature on, and then we need to multiply that by 2 to create all possible variants for the multi-compile shaders. So let me show you this in an example in Unity. So in this case, we have this simple shader. Again, it's a shader. I don't know why another Unity was needed, but OK. So you can see, same example I showed you before, a simple shader using these keywords. Remember that in shader graph, you can also create keywords. And if you go to Unity, let's save some performance here, and you select your shader and go here in this button right here, you can see that first, if you have a skip and use shader features, you will see here all the variants that were generated. In this case, 4, the worst possible scenario. You can actually click show and display all the permutations that I was talking before. So in this case, you have all possible permutations. Why? Because in this case, I have 2 features, 2 materials using this shader with different features. Of course, in this case, I didn't did the shader editor script in order to display the keywords here to configure them. But instead of doing that, I will give you another piece of information, which is that you can put the inspector in debug mode. And here you can see the keywords that the materials are using. So one is using feature on, and the other feature off. So you can see where the problem comes from. So if I do feature on, so right now both materials uses the same feature. I reset the editor to normal mode and go to my shader. You can see that now it's 2 variants. We halved the number of variants according to a simple configuration. Of course, if you need the other configuration, yeah, you need to pay the price in terms of variants. But, well, that's a little bit of a balancing act. And again, if we go to show, you will see essentially the new versions of the variants. So what you can do about this information? Well, of course, first, as we just discussed, evaluate your usage of shader feature keywords in your materials. You might be using combination needlessly. Try to, essentially, some clients say that they create some kind of archetypes of materials to try to reduce the number of combinations. It's like you have 2 or 3 possible combinations, or 4 or 5, depending on the case, and try to respect that material configuration for different usage cases, instead of just randomly toggling on and off stuff. Then, if you are creating your own shaders and you create a lot of multi-compile keywords, consider if you actually need them for being multi-compiled. You can actually convert them to shader feature if you know that you are not going to toggling on and off the keywords. And consider if you actually need keywords at all. Sometimes using just regular if, or what is called dynamic branching, so essentially ifs based on uniform variables in your shader, you might save some performance, but it might not be a huge thing. So what you can do is try to move some keywords to dynamic branching and monitor the performance on the GPU to see the impact of this in the lowest target device you are targeting. And check especially the occupancy of the GPU to see if that might be the actual issue or not. And you can do this work manually by modifying the shader on your own, the final shader, or automatically, since Unity 6.3, there's going to be a feature that allows you to configure which keywords you want for them to be compiled as multi-compiled shader feature and dynamic branching. Essentially, that will override the default shader type of keywords. If you want to get more information, you can go to the shader stripping fog Unity 6.3 manual page that will have some information about how to do this. But well, you can add another layer of shader stripping on top of this, which is by using the iPreprocess shaders API. This interface allows you to get a callback whenever a shader is compiled, and you have the will to reject shaders that you know that you won't need. So again, based on your own knowledge of your own shaders, you can reject variants that you know that will never be used because certain combinations you are sure that will never be used. Or if you follow the advice from last year's talk, we discussed how to detect which shaders are actually compiled in your game, are used, and you can generate essentially a graphics state collection asset containing the list of these shaders. You can do something like skip any shader that is not in the list of shaders used by my game. That's an easy way to do that, but consider that you might, if you are not very diligent with the way you collect the number of shaders your player uses, you might be stripping shaders that you actually need. In that case, Unity will automatically pick by default the closest shader that matches your requirements, the keywords of your material. But that might trigger lots of glitches and issues that you might not expect because maybe it's not the exact shader you need and you might have a feature that you don't need enabled. So when you do this, consider, at least for development builds, to build with the strict variant matching option on. That will essentially make Unity display magenta in any case it doesn't find the exact shader you need. And consider that SRPs like URP and HDRP implement their own versions of these strippers using the iShader variant stripper interface, which essentially is a SRP-specific variant that essentially allow these assets to strip variants based on SRP asset settings. So it will analyze which settings might tell URP or HDRP to discard certain variants. For example, in this list, you can see some of the HDRP configurations that are taken into account when doing this automatic stripping. Like, for example, if you don't need distortion or motion vectors or decals, those variants will be stripped for you automatically if you have that disabled in all the SRP asset settings. Remember that you can have different assets according to different qualities. This will evaluate all quality levels and see which features are disabled in all the quality levels. And again, I recommend you to check anything that implements the iShader variant stripper to get to know how this works in more detail. For example, in URP, the class that implements this is called shader scriptable stripper. And you can see all the conditions that will strip shaders for you. And more tips about shaders. This is a big thing. One thing that you can do to go even deeper into this analysis is to use the Unity data tools. This is a command line interface GitHub repository that Unity made that allows you to generate a SQL database with lots of information of your asset bundles. This only analyzes asset bundles, so addressables or manual asset bundles. And if you are using dots, the content archive files, it provides some information for the content archive files of dots. So that's another thing you might want to take into account. And the idea is that you can use into this SQL database a query like this one to get to know the number of times a specific keyword is used in all your shaders. So you can focus your performance optimization on specific problematic keywords. Also, if you are defining your own keywords, remember that by default, Unity will assume that the keyword will be used both in the vertex and in the fragment shader. But you might only need to use a specific keyword for fragment shader, for example. So you can define the exact stage a keyword will affect to, again, shrink even more the number of shaders. Remember that vertex and fragment shaders are considered two different shaders. Also, if you have a lot of graphics APIs in the player settings, like Vulkan, OpenGL, DirectX, and so on, you might want to remove the ones that you don't need because we need to generate certain variants according to different graphics API. The shaders for OpenGL might not be exactly the same as Vulkan, for example. So if you have extra graphics APIs that you know you don't need, just remove them. There are some specific cases like DirectX where this cannot happen, but the general idea is try to do this. So finally, let's discuss the final topic about asset loading and how Unity loads stuff and how you can get to know what is slowing down your loading times. So essentially, whenever you ask Unity to load something, a scene or an addressable that is being loaded, Unity will start part of the loading process in the background, in the loading threads, specifically the preloading manager at the beginning. This is a parallelized thing, meaning that this won't interrupt the main thread, but it's a single threaded, so you cannot load assets in parallel. It will go one at a time. And also the dependencies of the assets are loaded, so if you load a scene, you will load the prefabs, the materials, the textures, and so on. So the first thing that this background thread does is to deserialize the assets objects, meaning that it will deserialize the mono behavior, transforms, the game objects, every single C# or native object that Unity might need. So the first tip about this is try to reduce unnecessary game objects. For example, if you have a heavily instantiated prefab in your scene that has a lot of these objects that act only as folders just for organization purposes, you might save a lot of loading time by just removing that and trimming your hierarchy structures of your prefabs. And for example, if you have a lot of instantiated skin objects, characters running around, you might want to use the optimize game objects property in the FBX importer, in the rig tab, that allows you to essentially skip the creation of the bones hierarchy, game object hierarchy. Because you might not need to do that, to have them at all. Or maybe you want to have that just for the hand, to attach a weapon to the hand. You can expose specific bones, at least in a read-only manner. You cannot modify the bone's position, but you can read where the bone is. Then, the next step after deserializing the objects, or in the middle actually between them, is to load the content. Certain assets like audio, FBX, models, textures, the object of these assets might be slim, but the contents, the texture data, the audio data, all of that might be big and might be handled differently. So for example, you can see here in the preload manager how a sound is loaded because it has the classic load fmod sound. That's an audio that had the preload data option checked. So if you uncheck that, the preload audio won't happen during loading. Beware that will, instead, you will move the preload audio to the first time you play the asset, so you may experience a spike during gameplay. But an intermediate that you can do is not doing that during loading times to allow Unity to load faster or your scene to load faster. And then in background, you can call the preload audio data from your audio clip to manually say when you want to preload the audio. And you can, time slice, do one at a time or something during gameplay. Then the other thing that is in charge of uploading data is the async upload pipeline. Essentially, this is in charge of uploading mesh and texture data into the GPU. And this has some settings that allows you to affect how it works because it is done in the render thread, actually. It's commanded by the preload manager, but it's done in the render thread. So you can say something like the time slice, how much time you want for it to take. So you essentially, if you're loading behind a loading screen, you might want to bump this as much as possible because you don't care about some spikes during loading times. But if you are doing gameplay, you might want to reduce this. Also, you might want to check how much memory you devote to this, because the more memory you have, the more data can be uploaded at the same time, but of course, the more consumption you will have. So you have a lot of information about this in the blog, or the Unity blog post called Understanding the Async Upload Pipeline. So I recommend you to read this to get more details. And also the shaders are loaded. So here, again, another thing that shaders affect. So the advice we just saw about stripping variants will also affect this and improve your loading times. So that's what happened in the background. But that's not the end of the story. After that, we need to do what is called the integration step, which is the act of doing the loading operations that cannot be loaded in parallel. Some integration operations might require some Unity APIs that are not multi-threaded friendly. So part of the work happens in the main thread, like, for example, calling the awake and on-enable of your scripts. And remember that assets also have on-enable callbacks that might require some initialization. To control this, you have the application background load priority API that allows you to define, again, how much time you want to devote into integration per frame. It allows you to time slice the integration phase. But consider that this has a per object granularity, meaning that if you define the time slice to be 30 milliseconds, and you can load 5 assets during those 30 milliseconds, great, those can be loaded. But let's say that the integration of your main scene takes 10 seconds. that won't be time sliced. So we load one, essentially we integrate one asset, and then we later see if we can time slice. Certain specific operations might be able to be time sliced, but specifically load scenes is one of the cases that won't be time sliced. So again, same advice I gave you before. You can change this setting to make the time slice as big as possible when you are in a loading screens and you don't care about spikes, to let Unity load as fast as possible. Or if you are streaming pieces of your game as you walk around like an open world game, you want to reduce this time slice to not affect too much the gameplay. And of course, the loading will take more time, but in this case, you usually don't care about that. And for example, regarding the thing about not being able to time slice the integration of scenes, is that if the big problem of the integration of your scenes is calling awakes, starts, or enables, you can manually time slice. You can essentially disable every object in the scene, and essentially once the load finishes, enable them one by one on your own to kind of have a middle ground solution. Of course, the other solution will be to split your scene in multiple scenes, but well, that's depending on your scene structure, what you will do. So let me show you a capture with this. So I have prepared one. So I will skim the profiler to find anything that is using the loading threads. So you can see that the loading threads are using these frames, and about here it stops being needed. So here is the first frame that uses the preloading thread, and probably the previous one as well. Yep. You can see clearly my loading scene update method that essentially loads scenes. And immediately the loading happens in the preload manager. And again, it's not interrupting the main thread. So you will see some files being open and essentially headers being read. At the beginning, you might skip those. But as you go, you will see some things like this marker right here, loading read object threaded. You can see exactly the material and the name of the material that is being loaded, the operation that is being done, in this case, reading the file containing it. There's certain addressable settings can improve this, but let's leave that for another talk. So you can see lots of materials being loaded. If you skim, you can see, for example, here shaders being loaded. So there's a part of the shader loading. This is not yet compiling. That's another step. This is the loading part that happens on the background thread. There's some things that will happen in the main thread as well. So you can see shaders are a problem almost everywhere. And if you go away, if you continue seeing about here, you will see that at one point we will switch the preload manager to the wait for integration step. So it should be about here where the load scene operation, you can see how pieces of the scene are being loaded right here. And again, objects like mono behaviors and whatnot are being loaded. And interestingly enough, some callbacks are called here, like on after deserialize. But you can see here how the background loading threads say, I'm done, I finished, now I'm waiting for the main thread to finish. So you can see that probably the previous frame, no, this frame, you can see the integrate markers on the main thread, and you can see what's happening here. In this case, again, loading shaders, which you can only strip them to reduce this cost. Loading shaders, and about here you can see the integration of the scene. So maybe you will want to also pay attention to this, because this is essentially what we call on enable, awake, on disable, and whatnot. Of course, in this case, I have a lot of just-in-time compilation because I didn't compile with IL2CPP. But the point is here that you can see how most of the integration of the scene is taken by on enable, awakes, and whatnot, which is the thing I mentioned before. You can disable this and manually enable them in a time slice manner. So essentially, when you are loading times, remember to check both the preload manager to see what's doing, what objects you are loading, how many of them. You can recognize something that you might not want to load. And then check what happens on the integration threads and modify the settings I mentioned before to kind of reduce this cost. So well, guys, that's it. So essentially, as the main takeaway is something that is easy to miss, but in some cases you might save some performance by taking into account that the intermediate textures can be an issue in your game. Remember that script compilation might be improved by checking domain reloads and cleverly split your assemblies. Remember that shader stripping is an issue all around, and it will also affect build and loading times. So take stripping very seriously in your game if you want to have high performance of the editor and iteration times. And also regarding iteration times, profile loading times and take a look at all the details to try to improve your scene, your game responsiveness. And finally, material loading is something that I highly recommend, especially in HTRP projects, to reduce as much as possible draw calls and essentially set pass calls. So thank you, everybody. Here I leave you the QR code for the consulting services email. If you want, if your company needs some help regarding performance, you can contact us there. And me and another consultant will be in the performance and optimization stand right next. So feel free to pop in and ask any question you have. So thank you, everybody.